Hello, my outstanding friends. Roger Spur once again. And I'm getting a little more aggressive with my claims about the things that I have discovered, which is primarily this one here is the big one, which is dark matter, electron flood theory, which replaces the standard model. And what it does is it changes in a very fundamental way. Originally, one proton was just one thing and it couldn't be broken up. And then they realized if they hit them hard enough, they could smash them into bits. And then they started hitting them head on and getting all kinds of debris. And they dug through it and they found those two particles as the smallest particles that exist. There's other bigger particles, but it's called a particle zoo because there's so many particles. Now, they say, though, a proton is just really like a big glass ball and you can smash it into all kinds of things. But the smallest thing that they've ever seen is these two particles. They can actually see them. Now, my claim is that electron flood theory, dipole, it's dipole electron flood theory. And I have some papers written on this. I've known this for many, many years, but I couldn't prove it until we were able to actually do this and show these particles. And what it really is a proton is made of 1,823 of these particles here. The two of them together make what's called a Dirac neutrino, a gluon. All right, it basically was an electron, but they never knew the dark part was attached to the electron. So in a proton, there's 1,823 of these particles. Now I'm going to show you this in so much detail. I want some physicists to confront me and say, no, Roger, here's why you're wrong. Because I can say, no, you are wrong because here's why I'm right. Now, one of us has to prevail, or we can come to a standoff. I don't know how it's going to end up, but I can tell you what, I am not able to be heard now because I'm being denied. Like right now, I came up here to try to comment on NASA. And I came up here right away, and I put my comment in. And there's 0 comments. And what I'd like you to do is come up here. It's called Expedition 70, astronaut Laurel O'Hare talks with Cake TV, and I'll put a link to it and see if you can get into this. I can't get into it. I don't think. Well, I know I'm blocked from most of them, and I've never had any responses, and I've tried over and over and over to get my information because I'm going to show you. I think we can get free energy out of this. I really honestly think we can, and it's at least worth a look. Because I will show you the particles that we need to charge up batteries. They have no weight whatsoever. They have all the energy. And that's exactly what we did, is separate the ones that have no weight from the dark matter that has all the weight. Dark matter is 95% of the universe. And they know it's there. They just don't know, they can't understand it with the standard model. It should not exist. Well, it can't exist with the standard model. Let me show you these particles, how I can stand behind the statements that I'm making. Because I'm a material scientist. I'm not going to tell you anything unless I have something that supports that statement. All right, so let's get started. I'm going to support every statement I make. So let's get started. This next clip is only 2 minutes long, and it makes my claims very clearly, very quickly. And then I will get into it very deeply. So let's get started. Happy New Year, my good friends. Huge claims this morning. I claim we discovered dark matter, and there it is right there. This is from CERN and Fermilab. These are the smallest particles they can find, but they find them in showers and don't know their origin. We used light, and we can see their origin. Identical same particles. We accelerated light, we split light and broke the black from the white, and we created fission and fusion. That's my claims. Have a sterling New Year. Okay, my friends, couple things going on here. I probably got things a little bit out of order, but I'm going to try to do the best I can with it. I am going to show you that the black separates from the white in these particles that I claim we're showing as light. And the black can separate from the white, and an atomic bomb blast is exactly what it does. And I'll show you that coming up. And there's what they call a Whistler wave in front of the main concussion. And again, I probably got this out of order, so I'm maybe going over things a couple times. I don't know. But this is what you're going to see, or you hear this first. It's going to go, brrrt, and then you're going to get this house burned down, and then it's going to knock it down. And again, then after that, I'm just going to explain my theories and how they relate to, the atomic model. Oh, one last thing. Towards the end, it gets real quiet. You're going to have to turn your speakers up quite a bit. And I don't know what happened, but like I said, I got interrupted a bunch of times, and I don't know what happened, but it got quiet. So just alerting you, that's all. All right, this is going to be the atomic bomb blast. This is one I did a couple of months ago and put up here. So the sound's going to be kind of terrible because I'm playing it from my PC. So here it goes, but you'll hear exactly what it is, and I'll probably cut in here and there it goes. First thing you're going to see is the detonation go off, and you're going to hear, brrr. All right, let me turn this up so you will hear that, because it's not loud, it's just a rattling sort of sound. They call it a Whistler wave, and nobody's ever been able to explain it. Here it goes. Did you hear that? You didn't see any nuclear blast yet. You can see it, but now it's coming at us. You see this? This is the dark particles coming at us. That wave coming across the desert. So we have not heard anything other than that. Now we're going to hear the blast. That's the blast. All right, now listen. Remember we heard that ba ba boom. Now listen to what happens after that. Because there's the dark particles hitting, but they have to come all past us now. You hear them coming? It's like a wave, a gigantic wave of these dark particles all by themselves. They're trying to catch up with the white ones. You hear that? That's just an amazing amount of motion. On and on and on here. Now it's starting to taper off as they go past. That you would call dark energy. There's no white particles attached to that. When the white particles have already gone and been pushed away, and the black ones are coming out trying to catch up to them, basically. And here's the thing about Whistler waves. Anyway, I'm going to just keep going with this for another minute or so. All right, I'm just going to cut to the chase. You can look up the details. These are Whistler waves, are electromagnetic waves, but they occur at audio frequencies. You can hear them, but normally light, you can't hear light normally. This you can because of the way it's being emitted. It's being pushed ahead, bouncing back and forth as it goes forward. That's all right. Okay. Don't freak out on me. If you are capable of nailing a nail into a piece of wood with a hammer, you can understand this very, very simply. What I'm going to show you is, this is from atomcentral.com. This is the test house from a place, this was the Death City when they tried the nuclear bomb blast in the desert, and see what it would do to all these vehicles and poles and wiring and houses and all this stuff. Now, I'm not sure how close this was. I don't think this was too far away from the actual detonation site. The people were a long distance away. I think they were 6 miles away when we heard that bang, and then about, I don't know how long it was, a little while after, bang, you hear the shock. Well, what we're going to see is this house is just going to smoke up. It's not even going to move. And that's because the electrons don't move. I never could figure this out. This drove me freaking crazy. But now I understand. It's the Kashmir effect. It's just shaking these molecules. And the black comes and pushes it away. It's like this coming up, and going boop, 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 and pushing other electrons. They don't go anywhere. They just swell up because of that Casimir effect, and they occupy more space, and that creates more heat. It's the only thing I can think of, because nothing even moves. Now watch. Here it comes. The bomb will go off, and you'll just see this thing smoke up. Wires will smoke up. The poles will smoke up. Look, it's just smoking up. Nothing's going anywhere. Look at it. It's just smoking up. Everything burnt off. Boom, there goes the house. That was when the black came. So this had to be very close to the detonation site, I would say, because pretty quick the white's gone and then the black hits. They're way out there. We saw the white, and then a long time later the black hit. So all right, so anyway, that's enough of that. But I hope that was pretty understandable. The first part is the Whistler wave, which is the audio sound. That's in where you can hear it, that, and then nothing until the black hit, and then you could hear more, like it was almost like a tornado coming through there. You hear more of these black particles, because the white crusts. What happens is, well, hold on a second. All right. This is the two possibilities that I see, is that when you make protons or molecules bigger than an electron or light, when you start to get up into 1823, 1824 neutrons, protons, which would be a hydrogen, I believe all the black goes to the center, and the whites surround it and try to get into that black. And they hug up to it tight as can be, and that they call it a proton. Now, it could be that, where all the black goes to the center, and all of the white particles go around it. You know, of course, they're red here. Or it could be like this, where it's layered. I don't think it's like this, because I can see the white particles can so easily separate from the black. And the black couldn't care less about being on top of itself. The black will just lay right on top of itself. It couldn't care less. It doesn't emit, it doesn't absorb, it doesn't reflect, it doesn't do anything other than attract the white particles. So I think that all the blacks are in the core. And then you do have this effect where the tightest ones to the core, in other words, the tightest ones that are going to be down around here, their core, are going to be the blue ones that have all the energy, because they're the tightest held. Then the next surrounding, like eggshell, would be the green. But I don't think there's going to be a layer of black between them, although I don't know. But the blue would be the tightest one, then the green, and then the red would be the outside, which the red is sort of loosey-goosey hanging around out there. And then when you put these in a pressure situation, it changes the tightness of these electrons. And that's what they're doing, pressure-driven ionization. You're just forcing so much more in there, you're driving them off. That's all it is. They're putting 92 or 190 or 184 lasers all going into the center, pushing more and more electrons, because that's all the laser does. Well, it puts light, and light is, each one of these particles is a four-banger. Again, like I said, it's going to take a little while, but this is what light is. Where are you, light? There's some light right here. This is what light is. That's a photon right here. This is the colorized version of it, so that we can see the energy levels. When it's going this way, that one right there is pushing hard against little particles that are in front of it. So it gets glowy. This one gets dim, because it's blocked by the black one. As this one gets full charge, it'll be just so hard, it'll flip to the back. This one will come to the front, so it'll just kind of continue down the road, sort of spinning as it goes. One charges, the other one takes over. That one charges, the other one takes over. Charge, take over, charge, take over. That's what the spin is. And that's what happens with this. Now, because they can get big and they can get small, at the Venturi, it says, well, I'll get small and just squirt right through there, because this is the pressure. This black wave is just an amazing amount of pressure, as I showed you right here. Look at that. That created the identical same effect as a nuclear bomb blast. No difference whatsoever. The black is pushing the white out in front. We'd heard, way out here, we heard, and that would all be gone. And then a second or two later, this burns the house down, and then the black stuff comes. No difference whatsoever. None. Zero. Okay, another one of my claims is light is literally a fluid. It's the same as fluid. And a venturi causes compression of light, in this case, and it causes extreme pressure inside the venturi to change. So you come in here, a high volume, and you come squirted it, all of that's got to crush down. And these fields, when you crush them, they just get powerful as hell. And the black can't get through, so it goes swat, 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 swat. And that gives you the compression. Now, we could adjust that number of swats, and we can adjust the intensity of the laser, and we can get enormous amounts of energy out of there, I think, literally for free. And if we could do that, we could create this particular style of situation. And Lawrence Livermore is talking about doing the same thing I'm talking about. These are low energy showers down here. These are the high energy showers, the big white showers as they come through. This is the muons. You see here, look. This is Lawrence Livermore. These are the muons. They back off here, just like I showed you. These are the electron showers. They come through very low energy, and then they come way up high as they interact with all the other particles that are in front of them. And I say we shine a laser through a venturi, which has got to be tuned right. That's the key. When you tune it correctly, you'll just get white coming through. When you get the white coming through, you absorb it into basically like a solar panel. And this is just all by itself, sitting there. Just very, very, I mean, there's no more simple setup than you can possibly have. And you should be able to carry it around in a little lunchbox like this. This is, of course, a Geiger counter, but this size of a little device you could carry around handheld. And I think you could get a lot of energy out of there. I mean, a lot. Because all we're doing is stripping the white off. And that's all you want is the white. All right, so we're stripping the white completely away from the black, which is an electron shower. Electron showers are in the billions to trillions of electron volts, starting from, let's say, millions, up into the billions and trillions. That means an increase of hundreds of thousands of times, possibly. So whatever we come in here with 5 volts, you know, or 1 amp or 5 volts or whatever it is coming through here, it's a quantity of these electrons. We may get at least 200 times more. It should be minimum 200 times more than we started with. And it weighs nothing. It weighs zero. It's and we'd be slapping it down into squirting it down into a battery. And you don't even hardly need batteries for something like this, because this is a continuous flow of energy. As soon as you turn it on, you're just going to be harvesting just like you had a solar panel here and just be sucking up all that juice. So if you're getting 200 times, you just use a little pinch of it, come back here, keep it going, and all that excess, you run your car, do whatever you want. And these huge batteries, first of all, they're dangerous because they're explosive. And secondly, they're heavy. It makes a car heavier than hell. And if you get hit by one of those, you're in trouble. And the key here is, this is the only thing that you want to put in your car to make it to drive. If you take gasoline, right, you fill your car up with gasoline, it could be 60 pounds, 60 pounds of gasoline to fill your car up. This takes 0 pounds, 0 pounds. However, to pull the white off of the black takes a lot of energy normally. Here it takes none. This is the cat's meow, my friend. This is the top of the top. We're getting that stuff just separated for free. In a generator, you got to rip that stuff off of there. You got to pull the black away from the white so hard that the energy you put in sometimes exceeds the energy you get out. Well, it always does. This is the only way you can get more energy out than you put in. Okay, this is also my claim. A proton is not made of one big ball. It's made of 1,823 dipoles. It's called dipole electron flood theory. And I will prove it, and very hard to dispute. And I think we can get free energy by using strictly the white energy that comes out of the split, which is the fission and fusion. And that's electron showers, and electron showers are the cat's meow. If you can do that, which we did, and split them and created a muon electron showers, they claim that you should be able to get free energy, so I don't see why not. And a very simple design. That's my claims. Okay, so you say, why is this important that we can create electron showers? Well, these are the smallest particles ever found. That one has all the energy and no weight, and this is what you put in your car to make your car run. It has no weight whatsoever. You charge your car up, and if it weighs 4,000 pounds fully charged, you drive around and drain it, it still weighs 4,000 pounds. You put a bunch more of this white stuff in, it still weighs 4,000 pounds, but you can drive for another 500 miles. And that's this white stuff right here. These are the particles they found at Fermilab and CERN. But they started with huge particles to begin with, so they don't know where they came from. We know they came from light, and we know that if we do this, which we did, put it through a Venturi, which is this right here, and this is all going to be extremely well explained, so don't get worried. We accelerated the light, which is the function of a Venturi, to do acceleration and compression, and we compressed it, and pressure ionization is the thing they're talking about now, and this is pressurized ionization on steroids. Not only that, the black separated from the white, which is fission, and this is fusion. Right here is the stuff you want to put in your battery, and I think we have a way of doing that very, very simply, and it's this. Shooting that laser through that Venturi into a receiver. Now, you could have thousands, literally thousands of these little devices inside of a box that size. These are microscopic, but coming out of them is a full blast of white energy, and that's all you want. Now, Lawrence Livermore did the same stuff. Differently, though. They used something a little different. We used light, so we're way ahead of all of them, because we started with light. They started with huge particles. They started with this, smashing them together, and they mean nothing at that point, because all you do is get a lot of energy for a second, and then it's gone. We shot these particles, which is the light, through the Venturi, and we can do this all day long. And then you collect them on the other side. And don't forget, the white is the only thing that you want to charge your batteries. And there it is right there. We broke the black and the white apart. The white is the only thing here. We harvest it right there before it reattaches. We're golden. That's called an electron shower. Muon and electron neutrino, the black and white together. They come through the Venturi. The muon goes on its way. Well, it doesn't go anywhere. It can't get through. So it backs off. The white can get through because it can squirt down. You see the size of them here? This is the different particles. Where are they? There's the particles right there. They're the same particles. It's just that they're attached together. They never knew that. So when they come through here, the black one has to stay because it's too big. It's a fixed particle. The white one can get small or big. And it gets going through the Venturi, it gets very small. It goes right through. So that is electron showers. Now, let me show you what it means to get electron showers. And that's what they're trying to do right now with Lawrence Livermore. But it's just, well, I'll show you. You see this? We're using photons. We're starting down here with the neutrinos and smashing to bits, getting 100 gigavolts electron volts to trillions of electron volts. Now, they started with proton-proton collisions, these huge things, smashing them to bits. Then they have to decay them. And then they decay them down to neutrinos and antineutrinos, and then to electrons and muons. And then they get down to this point where we started from. And then we can do this all day long. So this is a breakthrough as far as I'm concerned. Okay. What I have to do is show you what they think is happening in the subatomic world and what I think is happening. And what I think is happening is shown by these actual pictures of light. These are actual pictures of light. These are not like this kind of stuff. These are really actual pictures of light taken with CMOS. So I have very good support for the things I'm going to be saying. Now, they are using pressure-driven ionization. I agree with that 100%, because what we did was the same thing. Pressure-driven right here. That's pressure, and that's ionization, which is the white separates from the black. And that's what they say. They want to separate the white from the black. That's what ionization is. And we did it, as I can show you, very, very simply. Normally, this is not an easy thing to do. They're using these gigantic colliders. All right, so they're trying to relate this to stars and planets and all this and how they form. Well, I think I know how they form, because dark matter is the gravity. And I show you the dark matter is those black particles. Now, they say scientists conducted laboratory experiments at the National Ignition Facility at Lawrence Livermore National Laboratory. It generated extreme compression necessary for pressure-driven ionization, crushing it until the little particles go flying off. Their research provides new insights for atomic physics at the gigabar pressure, which benefits astrophysics and nuclear fusion research. Okay, nuclear fusion means where you break something apart and it comes back together, or you don't have to break it apart, you just crush it together. That's what they're trying to do with molecules. We separated them and then they come back together. It's a little different because we created the fission. Well, here it is. We created fission and then fusion. All right, where is it here? All right, this is when it breaks apart is fission. That's what fission is. And this is subatomic fission because the two broke apart and the black can't get through and the white went by itself. I never thought this was possible until I actually saw it happen. I always thought the black and white had to be stuck together. There was no way you could stop it, but I was wrong about that. Now, I got a ton of stuff on this, and this is what they're doing at the big places. They don't realize that this is not one big ball. That big ball is just like this. Whoops. Except it doesn't have that in there. Wait a minute, I gotta get that thing out of there. These things get stuck together, man. These little neodymium magnets, yikes. All right, here we go. All right, out of the way. Now, this is a proton. But a proton actually is 1,823 tiny little dipoles. All right, every one of these is a dipole magnet. 1823 is here. All you do is take one more and add it there, and it makes it 1824, and it becomes neutral. So it doesn't want to give one up or take one on. When they're uneven, I don't care what unevenness they are, if they're not a neutral particle, and there's only certain areas where they're going to be neutral, and it appears for some reason, I can't tell you why, but at around 1823, 1824, they get basically stable. And then the next time they get stable again is another 1823 or 1824. For some reason, those are like building blocks, but those building blocks are made out of these particles, if that makes any sense to you. So one of these and one of these. When they hit these together, they get all this stuff goes flying. So they got bits and pieces everywhere. They got X's, which is just a big gigantic thing, and that'll kill you. And then they got all these other ones that are little bits and pieces here and little bits and pieces here and pieces here and pieces there. That's what they're digging through to find those tiny little particles that they did find. And they know that they're the smallest particles that exist, which is these. And those are the same ones we found too. Only we started with light, so we didn't have to dig through all the debris. That's the key. And we didn't have to do all that stuff. All we did was work with the light, which is, let me show you something. Hold on one second. All right, like I said, we're going to get kind of deep, so I'm just going to give you a real quickie. This is the pulse red laser, pulse, pulse, pulse. The particles have a huge field surrounding them, like way, way, way bigger than the particle, which is this field. The particle is this size. So we accelerated this and made it pull the particle right out of the way from the acceleration. That's the particle accelerating. Bam, at the venturi. The black cannot get through, only the white gets through. When it comes out here, we have all the Higgs fields. This right here, going this way, is this, we're looking into it. All these Higgs fields show up. These are the actual particles. This right here, this beam, is this beam here. Now, this is when they actually turn into photons. These are actually neutrinos, and I can show you the beam coming. The only reason these are good solid photons is because they're exactly in line with the Venturi, which is here. There's a whole ton of other ones coming too. You see them? They're all over here. And the only reason these ones are glowing is because they're not being accelerated. This is glowing because of the acceleration. These are glowing because of the reverse electromagnetic field. Look at the tips of them glowing like crazy. This one's just starting to glow a little bit, and here it gets crazy, yes. And here's where the explosion. This is a subatomic nuclear explosion. It's exactly what it is. Subatomic, smaller than atoms, nuclear because it's underneath the nucleus, it's within the nucleus, atomic explosion. That's it right there. And this can't hurt you because it's light. I don't think it can hurt you. And I know it can't hurt you unless you put your fingers right down in there or something, your eyeball, because it comes back together instantaneously. I mean, just within a zillionth of a second, it comes back. You see it right here? It breaks apart here, it comes back here. Maybe about somewhere out in this area, it's all back together again, and it's back to being just light. The black and the white do not want to be apart. The white is desperate to get back to the black. That's why in your car, you fill your car up with white. No energy all the energy goes in there, tons of energy. And it will burn anything, and it will push through motors and push them right out of the way so it can get back to the black. It wants to be attacked back to that black to attach to the black. It will do anything it can to do that. All right. So, and this also shows a point that the Earth itself absorbs all these electrons. If you get static on you and you touch a water pipe, right to ground. You get ouch. All right. If you touch electricity, it goes right through you to get to ground. That's why you have to ground everything. If the electricity doesn't go through the circuit the way it's supposed to, and it gets out of the circuit by accident, and you touch a wire or something that is hot, you'll get possibly electrocuted. But if it's already grounded, it will blow the circuit breaker. It'll just go zip, and pow, it'll blow the circuit breaker. And that's why you ground everything. So our Earth has to have more dark matter, in my mind, than it does white matter. It's the only possibility. And I look into ball lightning too, because that's a very, very interesting phenomenon, and it is real. And I understand that too, I believe. And that relates to having a dark core. Something similar to this. And attracting all the electrons so desperately want to get to that black thing that it creates a ball in the air. Now, that I'm working on. There's so much to this. I have to explain every single thing that happens. Like this right here, I have to explain this. How did this happen? What's going on? I can tell you exactly what's going on. This is the Venturi. This Venturi had a slit in it that allowed some black to come through. You see the black? Some of the black got through. You see it? The little black is coming through, but not much. And it's pushing the white desperately ahead of it. All right? Black pushes the white. You could call it the carrier. And they always did. They called it the carrier boson. I don't know why they stopped. And you see how pulsating this is here? Out here, this is what's called Whistler waves. If you look it up, Whistler wave. I don't know if they even talk about it. But a Whistler wave is only magnetism. It's only the white particles bouncing. And when the atomic bomb goes off, and I will actually show you this, when an atomic bomb goes off, you hear nothing at first, because you're way, way, way away from it. You don't want to be up next to it. So you're way back and you're watching. And they go 5, 4, 3, 2, 1. And you see the thing go off and you hear just like that instantly. Because this magnetic pulses work with magnetism in the air. They're not pushing any particles. To push a particle, it takes time. So then you wait a little while later and all of a sudden you hear bam, this black particle comes. That's the heavy duty one. And it takes time to get through the air, that's all. The white one takes no time at all. Right through the air. But this is not light. White is not light. White is the particle that is electricity. And it has no weight whatsoever. When you burn a house down from an atomic bomb, the house just it just smokes up. It doesn't even move until the black comes and then knocks it over. But in the beginning, it just completely combusts. But not the smoke just rises straight up like it wasn't even pushed by wind or anything. And then a second or two later, the black comes and there it goes. And again, I will show you this. Again, this is going to take some time. If you really want to understand this, it takes time. Okay, now, don't freak out. This is very, very, very simple. As I said, I believe this is the model that accounts for the atomic bomb blast. And here's why I say that. In an atomic bomb blast, they make these particles so big that they're already ready to fall apart. They just can't, there's just too many particles all in one ball. Now, which means there's so many white ones surrounding a black core. That's how I'm taking it. Now, when they blow that up, they don't blow it up from the inside out. They blow it out from the inside in, and outside in. And they force all those particles into each other, and then that's when you get that, all the white goes first, and then the black goes behind it. Okay, so you're taking all those in there like they're rubber balloons, and you're forcing them to get so tight that they take off like rocket ships. And then the black ones, they just sort of keep rolling down the road behind them because they're going to just follow. They want to be together. Now here's how I can stand behind that statement, because these are the ionization energies. When you're down here in the very low numbers, you need a lot of electron volts to pull them off because you're right next to the nucleus. And then a little more. These are your noble gases, basically. And the ionization energy keeps getting bigger. It gets less and less to blow the particles off. So the bigger the particle gets, the less tightly the particles are held on the outside. Once you get up into plutonium and uranium and all that, there's so many extra particles that when you hit there, boom, it takes off. And then you can see it sweep across the desert floor. All right, this is a little hard to explain, but I can just cut right to the chase. If this is one proton and they need a super collider to smash and break it, and that's hydrogen, why would hydrogen explode like a bomb when you put a spark to it? The reason is because you're adding more sparks into this, and then everything falls apart at once, and you get an enormous explosion, as I will show you. So hydrogen is not one big proton, it's 1,823 or 24 in a core of these dipoles. And you throw a spark in there, boom, they all go at once. Because they all break down. Every one of them becomes its own particle. All right, watch what's going to happen. He's going to explode this hydrogen-oxygen bomb, basically. And it's going to turn into water vapor and an explosion because all the extra electrons just all take their own space. So if it's this big when you started, when it was all boiled together, this is going to turn into a gigantic explosion. And that's why you hear it as an explosion. Now listen to this. This is unbelievably loud. And he tells the kids, keep your mouth open because you can blow your eardrums out. And they all laugh. They think it's funny. Well, listen.
How it sounded and compared to the sound you would hear. If that sound was too loud for you, keep your mouth open because then the pressure in your mouth
You see that? That's water. They're loving that. Now, here's the question. Cool teacher. Now, here's the question. If that's just one big proton, how the hell did you get that kind of an explosion? This is hydrogen and oxygen. How did that happen? It's because there's so many little particles that once you throw in that extra spark, because you could have popped that balloon and it could have just come out and it would just join into the gases. But when you have that in an enclosed vessel like that, and then you hit it with an extra batch of electrons, because that's what a fire is, it all goes off, combusts all at once. like electron showers of hydrogen. Basically, that's what it is. It's a hydrogen shower. All right, I'm going to try to explain what Lawrence Livermore was doing. And I'm not sure I'm going to have this right or not. I would like them to explain it to me if I have it wrong. They are shooting particles in here with all these really high energy lasers and accelerating them or doing something with magnets and so forth. And then it says, why do the muon events look like that? No, they're calling it a muon event. An explosion of base track numbers. I'm not sure what that means. But they're talking about getting into particles with a trajectory of trillions of electron volts through an emulsion medium. Now, they have 1,000 layers in this phaser. And I think they're trying to smash it through some kind of like metal or something that's able to give off electrons easy, hitting with these extremely high energy lasers. But to what avail, I'm not sure. Now, this is Lawrence Livermore again, and you can see the lasers coming in, and what it's hitting here, I don't know. Are they using a Venturi or something, or is it splashing off of a film of something? I believe that's the case. It's coming down and splashing off of something, hitting it, driving all of these shower particles off. But I don't think you're going to see the shower of particles, but I don't know if they're going to get any net increase. I don't know, because I really don't know that much about their experiment, because they are doing something different. They're using lasers, yes, but I think they want to skim it off of something that has a coating of extra electrons that they can just skim the electrons off. But I don't know if that's going to give them a whole lot of extra energy. Ours is a complete different setup. Ours is through the Venturi, right here. It's just right through the Venturi. And the light has to accelerate, and when it does, the black can't get through. In this particular case, now again, I showed one here where the black could get through, along with the white, and so we can see that it pushes. That's what it does. It pushes the white ahead of it. And these are and now out here is the Whistler waves. They're in the audible zone, and these are light waves. You know, you can't hear those. Frequencies a little higher. Now, the Russians did this in space, and this was back in 2015, I think. And I had some interaction with the Russians about this. I really didn't get much of a response, but I understand what they did here, and they didn't. And the same thing at Fermilab, he didn't understand either, Don Lincoln. Because here's Don Lincoln's stuff. Hold on, where was it? All right, this is what particles he found. And there they are. And at the same time, the Russians had found this black hole. Well, they didn't find it. They made it in a vacuum chamber in space with charged particles. And then that's when I realized all of this fit together. And so I got a hold of everybody, but it didn't go all that well. Hold on one second. I think I showed you this. Maybe I didn't. This is the Fermilab particles. Those exact ones that we found. No difference whatsoever. Standard model doesn't work. Basically, it doesn't. Now, just let's cut to the chase. He talks about them. And the last thing is, this is, in summary, the extended particles, the black ones, have a fixed size. They never change. He's right. They may have a fuzzy edge around them. Yes, the black has the color of the particle that surrounds it. Point-like particles are the mathematical extraction with a zero size. That's the white one, the glowy one. And I have to agree, I can't find any real mass to speak of. It says even zero-size particles, which is the white one, have an extended field. And they do, I agree with that too, due to the effect of the field surrounding them. But surrounding what? I don't know. This is Don Lincoln, who will not speak to me because he thinks I'm a tinfoil hat guy. And these particles fill space. And he also talks about that, the quantum foam. He's right about that. Space is completely saturated with these particles. And they blink on and off. He says right here, it's just like the head of a root beer, a dizzying display of change empty space experience similar activity, subatomic particles winking in and out of existence. These ephemeral subatomic particles are real and have a measurable impact on our universe. Yes, they do. These little particles, as every other particle goes through space, that's what causes them to wink on and off. They're hitting their fields. Bing, 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 bong, bing, 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 bong, bing, 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 bong. Sooner or later, light slows down. Light does not go at the same speed forever. And I show that in the light experiments too. We sped it up and we slowed it down. So don't forget, just what I just showed you. These are particles of light. Right? There they are. Just like he said, it's got a fuzzy edge around it. Yes, it does. Yes, it does. Fuzzy edge around it. Yes, it does. And these are abstractions. There's virtually nothing there. That's why when these hit the house, because they came first, the house just smoked up. It didn't push it over. It just invades the fields. Very strange effect. I'm still sort of having a hard time with that one. And then after that, the black one comes and just keeps sweeping across. And the house is in the way. Well, the house goes. And then you hear like a freight train coming through afterwards because it's just all the black ones come. And these are those particles. Now, when you're in the atomic range, when you're in these big, big particles like they're using, plutonium and uranium and all those big, big heavy jobbers, they're way up like this. When they go off in chunks like that. That's what really causes the problem. Our stuff goes off, it's very contained, and it puts out these. And these don't hurt you, the same as light. This is nothing more than light. Now, again, you don't want to be right in your face with it, but as long as you're, right there, I should be able to have that box right here, and be standing right here like this and have absolutely nothing happen to me, and have that subatomic particle captured as electric juice to make a car run. And because I'm showing, you could see there is a lot of action going here. There's a lot of juice coming through there. And you could, like I say, you could have probably 1,000 of those in that little package that I'm talking about right here. All right in here. You could have a ton of these. They're just tiny. And they could be in little blocks. They manufactured and just smack them out. Because all the stuff exists right at this minute. And again, same thing that Lawrence Livermore is trying to do right now. Only we could do it with a handheld. And then you could have all kinds of things. You could have 60 cycles, 50 cycles, AC, DC, USB, whatever you want. Any voltage. And portable, no grid, no nothing. You just plug into it. And this is no circuitry to speak of other than a little regulation circuit, and that's it. And I could think these should be, and this is a non-emitter of anything bad, nothing bad whatsoever. Not a single thing bad comes out of that. Nothing, zero. It would have no expansion, which is the problem right now. Anytime you burn something, the problem is our gaseous envelope. This is the other part they don't seem to understand. The gases that surround our atmosphere are pumping up like this right now, like a balloon. So as we spin through space, the outer atmosphere, the ionosphere, is scrubbing like hell, and it's getting hotter. And right below that, it's getting colder. And they think, that's, I saw a paper from Yale. They had it totally backwards. The out edge gets hotter, the next layer down gets colder, and then the next layer down from that gets hotter. That's what global warming is. There's zones between them. And I'll show you that. As a matter of fact, I'll show it to you because this is really important. That's another thing they don't understand. So there is, and the other thing is we need a new periodic table. Every electron, every proton has to be multiplied by 1823. Every neutron has to be multiplied by 1824. And that is going to be how many these particles, the atomic number is going to be. All right? You can still say what they're saying. there's only zones of stability, and we do know the zones of stability. I can agree with them on that. Like carbon's only stable at like 12 and 13, I think, something like that. But it goes way up this way and way down that way, and it's only stable in the middle. All right, let's take a look at that. All right, once again, this is very simple. Do not freak out on me. All of these are carbons. All right, they call all of these carbon. You say, well, wait a minute, how could they all be carbon? That's impossible. There are all these different things, all different weights, all different numbers, all this stuff, all different half-lives. The reason is, all it is more and more electrons. You see this? This is stable. See stable right here? That means the half-life, it doesn't decay, and it's stable. So it won't decay, so there's no half-life. That's why the whole thing is open here, stable. Now, the other ones have a half-life of so many, almost instantaneous. And then they call it the different kind of decay, mode beta and alpha and blah, blah, blah. Now, all you have to do is think about this. You see 12 exactly. Carbon 12 has to have exactly 12, and it's perfectly stable. When you go to 13, it's just a smidge off of stability. You see, it's a minus a half. And it's up here to 13, and it's still stable, they say. And then it goes 14, 15, 16, 17, 18. All that is just more and more electrons that they don't want. So they want to spit them out and come back down to stability. All right, so you go, and it goes way up here. All right, and it goes way more than that. They just don't know about it. Every one of these is a different number. See, 23, 22, 21, 20, 19, 18, 17, 16, 15, all the way down, exactly 12 and 13, basically. And then you go below that, and these, at that point, they're unstable because they want to add more electrons. All right, over here, they want to get rid of them to get back down to here. Here, they want to get some more to get back up to here, stable. All right, so I hope you understood that. And every one of these appears to be, I can't argue with it because I don't know enough about stability and measuring the stability zones, but I'll go with their stable states, yes. Let's call them stable states in every one of these. But those stable states are just more and more and more of these little electron dipoles. So we just have to replace the atomic number. That's the only thing that has to be changed is the atomic number. You got the atomic number is 1. That's not, well, actually, you could call it atomic number 1 because it's just element 1, element 2, element 3, element 4. So we'll call it element from now on. And the atomic weight will be the number of dipole electrons in there. So for hydrogen, it would be about 1825 right over here. 1825 dipoles. For helium, I calculated out, I think it was 7,980 or somewhere around there. But it could be element 2, that's fine. Element 3, lithium, beryllium, boron, carbon, nitrogen, that's okay. They can have that same atomic number because all it is next one more number. All right, but it has nothing to do with protons and neutrons. It has to do with total mass of dipole electrons. Now, this is how they're trying to create their electron showers, and it seems a little extreme. This is called the phasor detector at the Large Hadron Collider. Now, it's pretty serious here. They're shooting this particles and charged particles for a very long way. And then they're going through 100 meters of rock with the dark neutrinos, which are the muons, basically. And they will bang and bang, 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 because they're just nothing more than bowling balls. So if this must be some very, very seriously hard rock. And then at the end, it spits out phasors or whatever it does at the gigavolt up to trillions of electron volts. Now, if we can just squirt them out of these little device that we have, I mean, I don't see. This is 480 meters from here back to here. That's a long ways. 100 meters of solid rock. All right, and then what they're doing appears to me, this is the phasor right here. So they're banging into this solid rock, 100 meters of rock. And then they have this emulsion film right here, like a film that the particle goes through, and they can see the electron pulse come out of there. So apparently, or maybe they're looking for the dark particle. I don't know exactly what they are looking for, but I don't see where it's just necessary to do this. And it's certainly, I don't know what they're, all of this is a detector, apparently, is all they want to do is see if they can detect these particles. And we're detecting them pretty good right without what we're doing right here. All right, and they're the same particles. I mean, there's no way to deny this that I can think of. We started with laser light. Light is light. And the same particles coming, well, here, hold on a second. Okay, I know I've gone over this a couple of times already, but repetition never hurts. The dark particle, all the mass. The light particle, no mass, all the burn. That's the particle in its photon phase, and half of that would be an electron. We were able to squeeze and crush and separate the particles, creating the electron showers and a sterile muon. And we did it right here. And that's the particle being stretched right out of the wave because it went through a venturi. A venturi accelerates and crushes and pressurizes. All right, so that's that. Now, as the particle accelerated, it did this. This is the particle, and this is the neutrino phase where it's not quite up to a photon. And at this point, it has that characteristic to it. And then they tip up sideways like this, being pushed back. Now, these are directly in the line of fire here, so they have already turned into the photons. These, all the rest of them are not in the direct line of fire to the venturi, so they are in the neutrino phases. All right, so that's that. Now, the green ones are identical to the red ones. You see it? There's the green ones, no difference whatsoever, and the same neutrinos. All right, but much, much, much more powerful. But exactly the same design, architecture, whatever you want to call it. But here's where they are when they both come through the venturi at the same time. You see how weak that is? It just gets pushed out of the way. That one there is a rocket ship, and it reconcusses out there. So that shows you how much more powerful the green is than the red. Same particles, though. Just more spin to it, actually. The red has less of a spin, and the green is spinning faster, and the blue is spinning like a Z-rocket ship. And here it is right here. All right, that's when it's coming through the venturi. And by the time you're out here, you can see that there is two particles. There's two of the black and white together. Here, you wouldn't even know it. Over here, you would never know there was two of them. But because it's slowing down, so light slows down, light speeds up. All that stuff was untrue. All right, this is what light does. It spins. All right, that's what a spinning particle is. Light doesn't flap like a wave. All right, here's what we got. Hold on one second. Let me put a piece of light on the front of my light wave. Now, if you looked at this way, light's spinning. It's spinning. Sometimes it spins off to this side, and you get more going this way. And sometimes it spins off to this side, and it goes this way. And you see how it's a drill bit? You see how it's a drill bit? That's why one side it goes under and one side it goes over, that type of thing. Now, they all separate out here in these interference patterns. And it's not because it's a wave. This is a single slit. It's because these white particles hate each other. They say, you stay in your line, I'll stay in mine. And that's what they do, and I will show you that. Now, so this is what light does, it spins. Now, if you looked at it from the side, you'd say, well, this looks like a wave. That's all right, it looks like a wave, but it's a spinning particle. Now, blue is way down here. and then green is somewhere about here, and then red is way down here, slow spin. And that's why it's the angular momentum, really, the speed of the spin, that causes the intensity of the light, more intense light. All right, so that's that. Hold on a second. All right, take your time looking at this. That is the pulsed red laser. Again, the field of magnetism is huge. The particle is tiny. So the whole field, though, has to move through. That's why it's making that wave. All right, this wave. And there's a particle inside it. The particle has to push that whole big field through everything else. And all these particles, you see all these little dots in here? Can you see that? See all those little glowy dots? Every one of those is an electron. Every one of those is something, or a little gas particle or whatever, but it has a field of its own. So this field says, get out of the way, and these say, all right, and they glow, pushing back, and you can see them. There's no question they're there. Now, this, because it is the wave going forward in a direct, exact venturi straight through. It's got to be exactly here in order to do this. That's why these other ones, you don't see them. You see how this field is here? They're all over here. There's another one here, another one here, another one here, another one here. They're everywhere. They're everywhere. And they're all in here too. But you can't see them because they're not being pushed hard enough. This is pushing hard enough to be seen because it's going forward due to the venturi. But once the explosion happens at the venturi, the reverse radiation is so enormous that these glow with the brilliance, absolute brilliance. This one's not glowing much because it's just being accelerated. These are being exploded from the atomic bomb blast. That's a subatomic bomb blast. There's no other way to put it. And what you're seeing way back here is reverse magnet. We used to call it reverse EMF, electromotive force. And that's way, way, way out there. You see that? That's some serious, serious action, my friends. It's serious. She said, don't get much seriouser than that. Hold on. All right, don't forget, this is what they're doing at CERN and Fermilab with these big, huge particles. They should start with the small ones, much better. And here's what they see is this. They just see a bunch of debris. And they pick through it and they find that there's these little tiny black ones, these little tiny reds and greens and blues and all that. And you can see them here in their little picture here. See, they can see all these little tiny things, but they don't know where they came from. And big chunks sometimes parts of this and pieces of that. And yes, you're going to get all kinds of debris. But they don't understand the origin of all of that stuff is the photon. And that photon, as I showed you before, is nothing but this little particle right here. That's the photon. They're green or blue, every color is the same photon. I think I showed you all you need to see. This is the Higgs fields we see. I showed you the Higgs fields from CERN and Fermilab. This is looking directly into the venturi. And as soon as the white reattaches to the black, you get the Higgs. They have it just the opposite. They say the Higgs decays to a black and a white. No, the black and the white form together to create the Higgs. That's just exactly opposite the way it is that they have it. You want to see some Higgs? I call this Higgs on steroids. That's raw white. That's the exact total 100% raw white. And you see how that white particle is coming up here? And I believe they hit a black one and they just start to spin. And somehow it forces a field downwards instead of outwards. And I think the particle rides on the outwards edge of the fields. That's what I've taken away so far, and I think I can almost prove that because of a reverse spinner that hit a correct spinner, and it ripped off a particle off the edge, which was that was a stunner. That one took me years to figure that one out. This goes back 8 years, even more than that, 2013 or so, 2014. Not 10 years. All right, like I say, I have to account for everything. I have to try to account for everything. These are the particles, the white spray coming out this way. And eventually they hit something and they start to spin into these fields. It just happens. Now, this one here threw me for a loop. So I'm looking up saying, what the hell is that all about? And I believe instead of spinning this way, it's spinning the wrong way. Now, what correct way are they spinning? I don't know. I think it's a right-hand rule. Usually they call it. I don't know if that's right or not. But I'm telling you, this one is spinning, gathering the energy into itself, glowing more, instead of spitting the energy out like these are. Then I saw another thing, and I think it was this one colliding with one of these. And like I say, I think the particle rides on the outside edge and pulsates inward. I can't account for that, to be honest with you, but that's the only thing I can think of, because I don't think there's a ton of particles. I think there's only one particle. So that one particle creates a field. How does it create the field? I don't know. But it's a pretty good, they're all the same basic field. And I think it sits and rides on the outside. All right, remember I showed you that reverse spinner? The only thing I can take from this, all of these little white spritzes, is they're hitting these fields and causing them to spin. And this is the best one that I saw. That I think that's what's happening here. It's incorporating itself into that, causing this to spin, and somehow forcing the fields downwards into the core, which is the light disk. They call them the Higgs fields. And these white are coming through here, and they combine with the black to make these fields, which are the Higgs. So it's not the Higgs decaying to the white and the black. It's the white being separated and finding the black again and spinning like crazy, as you can see. And we got them coming out of our ears. And they're thrilled when they can get a handful of them. Look at this. This is crazy. All right, now, hold on one second. All right, now, pay close attention. All right, this has never been seen before, and that's the only time I've ever seen it. I believe this is that white particle I was talking about, this one right here. And here it is again. Because when you take these, you see a bunch of stuff at the same time. But what happened here, I believe this particle interacted with this disk here. Now remember I say, I think, the particle rides on the outside edge here. And it might just sit here, I don't know. It might just sit here and come forward and not spin. I don't know, I gotta be honest with you, I don't know how it creates this field. But they all have this Higgs field when the particles come back together. Now, this particle here came back together going backwards. You see, let's look at it carefully. Here it comes. And you can see some definition coming here. What it is, I don't know. But it sure looks like it came here this way. All right? So it's spinning here. Now, what happened? This one down here was spinning this way, in this direction. Okay, so it's spinning this way, which they all do. So it's spinning just like that. Now, what happened with this one? This one's spinning in the wrong direction, getting hidden into itself. And now, apparently, when it banged into this field, it's making a hit on this field. The particle, there's still a particle in there, but it was spinning in the wrong direction, is my thinking. So now, it interacts with this field. And this spins this way, and it grabbed a hold of that particle and ripped it right off the wave. It ripped it right out of it. And not only did it do that, it just stopped it from interacting anymore. See, the particle's gone. That's the only thing I can take from this. Let's think it over real careful. This particle's coming backwards, so it's spinning in this direction. Let me turn the lights on. It might not be as easy to see with the lights on, but at least I'll show you. In other words, it comes down this way and spins backwards, which is still on the outside rim. The other one's spinning this way, and his particle's on the outside rim, but it's normal. It's doing its job the way it should. This one comes in, this one grabs it and says, get out of the way. And it grabs it and twists it right off of there. It looks like it to me. And this was in like a half state between being backwards and being forwards. I can't tell you what. All I can show you is what I see, and you see what I see. All right, so this one here, the whole field's gone now. As soon as it ripped it off of there, it just faded off. That's what it looks like to me. So that's the first antiparticle probably anybody's ever seen. And again, I only saw it once, so I don't know. And there's another mind blower. This is nothing more than magnetic fields again. And this is the fields that surround planets and so forth, spinning, planets in space. And this is the moon, and the moon is crushing particles, turning them blue up here because it's not spinning, it's just going forward in this direction, compacting the light. They say everything's stretching, pulling, red shifting. Well, you could do that. If you ran away from the light, it would shift. You'd see it in a red orientation. But I don't think that's what's happening because everything's got to come through these fields. So all the light that's out there, they say it's going the same speed. It's not. It's slowing down. I showed you it slows down. It speeds up. There's no question whatsoever. And all these fields are all in space. They're everywhere. Literally everywhere. So where they think they're going billions of miles out there because of the speed of light, how much stuff is this light coming through? Where is it going? It's coming through something real dense or something real weak? You look out in the galaxy, the Milky Way, it's nothing but, well, it's like this. A little drawing of what it looks like. All right? Here we are in the sun. And you look out there, it's nothing but this cosmic microwave background, flinking on and off, like Don Lincoln says, blinking like the head of a root beer. Because every light particle coming through there is going to hit a bunch of other ones. And then go blink, 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 blink. And then they're just going to settle back there, called the cosmic microwave background. It's just not moving anymore. So they're getting hit every now and then. And then another one has to slow down. Now, think about this. Here's another thing they don't understand about global warming. On the sun, it's 10,000 degrees, the surface is what they say. And they have instruments that I can say they're probably pretty correct. Let's say it's 10,000 degrees. Way out here, so that's the edge of the surface. Way out here at what they call a corona, it's millions of degrees. Why? No explanation. Nobody can account for that. Now, on our surface of our Earth, it's say 100 degrees. Let's just round it off. And way out at the atmosphere, out of the ionosphere, it's 2,700 degrees. Right? 2,700 degrees. Why? Why would it be so hot out there? It's called the ionosphere because there's nothing but extra electrons, the ions, the white particles I'm showing you. And they are being created out there because we're scrubbing through space and our envelope is getting bigger and bigger and bigger. It means more and more scrub, which means more and more turmoil, which means more and more, hurricanes and floods and compression and all kinds of turbulence in the atmosphere. It's because the greenhouse gases expanding. It's not because they're holding the heat in. It's because it is expanding out, making us scrub harder through all these other particles. This is saturated with particles. There's no question whatsoever. The universe is actually packed. And the same thing, Don Lincoln calls it the quantum foam. I don't agree with that. It's just like a soup out there. So it's not empty space by any means. So if they're looking way out there thinking that light never slows down, they got a big thing to do. Now, what's crazy out here is it's 2,700 degrees out here, 2,700. Below that, the next lower, just below that, it's minus 80 Celsius, which I don't know, I think maybe it's 140 or something below zero, 100, somewhere around there. It's way, way, way below zero. So we go from 2,700 above zero to 150 below zero, let's call it. And then it gets hotter again down below. And the colder it gets in the middle, the hotter it gets below. The hotter it gets below, the colder it gets in the middle, and then it gets hot again below. That's the key. That's the dipole nature of this whole thing. That's what's causing global warming. And that's what's causing all of these weather patterns to be changing and all kinds of terrible situations going on with our weather. It's because of the expansion of the gases. Now, if we could do what I'm talking about and get free energy, and in addition to that, not expand the envelope of our planet any bigger, it doesn't get any better than that. So I think we have to look at this, and again, I'm shut off. I'm going to put a link to this. I think I was shut out of here. Whoops. Where is it? This one here. I was trying to comment on here. Zero comments. I'll do an F5 and see if anything changes. They got me locked out. I'm locked out of almost everything. Alright, here we go. Zero comments. And I'll put a link to this. This is NASA. Yeah, NASA video. I'm linked out of there. I'm linked out of Fermilab. Nobody will talk to Roger. So I want you to try to go up, see if you can get a comment on this one. And like I say, I'll put a link up here on my video, and you can try and look at it. All right, thank you. I love you all. I think I've shown about as much as I can possibly show and taken about as much of your time as you can possibly give up. Okay, India is sending a space probe to look for black holes. Well, black holes are nothing more than dark matter collecting with a crust around it. And the Russians did this, as I believe I showed, or I'm going to show it to you now, right here. I'm sure I showed that, but repetition can never hurt. This is in a vacuum chamber out in outer space in their space station. I think it was 2014, 2015, somewhere around there. And it's a vacuum chamber, very low gravity. There is a little bit, that's why it's squished, but because way out in space, it would be just perfectly round if there was no gravity, because this is still in a gravitational field. Now, the dark matter collected in the center, and the white particles collected around it. Now, if this dark matter got bigger and bigger and bigger and bigger, you'd get more and more and more white. Now, depending upon where it is scrubbing through, it's going to turn into a really hot ball, basically, with a dark center. And that's what a black hole is. And they said during the experiment, we contacted the Earth guys who couldn't believe it either. Now, I was not really involved in this, but I was pretty close to it. And I did contact the Russians about it. And I don't think I got any response that I can remember. But I also contacted Fermilab about this and finding their particles at the same time, saying, oh, this stuff is starting to fit together. I can see the white can separate from the black, and that was these particles here from Fermilab. And we found them. I mean, it's not really a big thing to debate about. So anyway, I guess I'm going to call it quits for now. Thank you. I love you all.